So thank you to the organizers for inviting me. It's a great privilege to be talks. It's nice we have a new draft of this paper, and I'm going to include some of the results in the talk today. This is our first opportunity to publicize them. So I'm concerned, like a lot of people at this conference, with generating provable random numbers. And a specific scenario, which we've seen, where this really matters is if we're using something like RSA. This could break down if somebody has a quantum computer. It could also break down for another reason. If somebody tries to generate a seed that's not actually random and uses it to generate primes, and those are known to an adversary, then of course the communication becomes completely insecure. And this raises this whole question about whether randomness is something subjective or objective. I've heard a lot of people discuss this in talks. The basic problem here is that Alice might think that her numbers are random, but an adversary, Eve, knows that they're not. And that's where the insecurity comes from. And we'd like to use mathematical proof to kind of do away with that issue. As far as existing solutions are concerned, there are industry standards for these. These are industry standards from America. And when we talk to people in information security and we ask them about randomness, this is the most common answer. They say they go by these guidelines coming from NIST. But what's worth pointing out is these are not really at the level of what I would call mathematical proof. They make assumptions about good faith efforts, faith in the source, initial faith that is kind of reinforced by certain tests. So the question I'd like to pose is whether there's a way of doing better than that and actually generating randomness, even if we don't have good faith in the source that we're using. This is a broad field, and there have been excellent talks on other animals from this species. This is the one that I'm going to focus on, untrusted device randomness expansion. This is the problem that assumes that we have, first of all, a small uniformly random seed, and secondly, we have an untrusted quantum device. And we want to carry out some sort of classical procedure on those two resources to produce an unlimited number of numbers that are truly and provably random. And the only assumption that we make that is the basis for all of our security assertions is the assumption of non-communication. We need to be able to assume that this device is not communicating with the outside world, and secondly, that we can, in a single round of the protocol, we can block different components of the device from communicating with each other. And that's crucial because we're going to be exploiting quantum non-locality. Okay, so results on this topic. So Roger Kolbeck in 2006 in his thesis proposed a protocol for generating provable random numbers by repeating a non-local game over and over again and checking the average score to see if it's greater than a classical device could achieve. Kolbeck's thesis makes some great reading, and what I found interesting about it was that the proposal as this phrase is very persuasive. It seems as if it should work, but no proof is given, and it was hard at the time, at least when I read it, to see what techniques would actually allow us to prove the security of the protocol. So that was proposed, and then it was dormant for a while, and then there was a key paper by Peronio and several other authors in Nature in 2010. They did an experiment actually carrying out the protocol, and they did an analysis from the perspective of a classical adversary. This happened to coincide with when I started working in quantum information. My talks are becoming more autobiographical because I'm on the job market this year. I talked to Yayan Shi a few months after I started working. He told me about this idea of untrusted device random number generation, and it was the weirdest thing I'd ever heard. We started studying it and started trying to develop our own techniques to attack the problem. So I wanted to call attention to one of the basic difficulties in actually carrying out a proof in this case, and that is the problem of the entangled adversary. If we're really going to claim that this protocol is secure in an absolute sense, we need to reach the standard of universal composability, and that means we need to deal with the possibility that an adversary might have entangled information with the device that we're using. And we need to show that whatever numbers come out are random, even from that perspective. The reason that's hard is it can occur that you have information that is useless to an adversary that has no quantum memory, but is highly useful to an adversary that does have quantum memory. And that is due to the phenomenon of information locking. You can encode information in a random unitary basis. If the adversary later learns what that basis was, she can decrypt it and get a lot of information. And we need to, if we're going to really prove security, we need to rule out possibilities like that. So there were multiple papers that prove security against an unentangled adversary. So provided that the adversary has only classical information, it was proved that these numbers are truly random. And the methods involved classical statistical arguments, generalizations of the central limit theorem, basically showing that if the device does what it's supposed to do, it will give random numbers. If the device fails, it will likely abort in the protocol. First paper to prove full universal composable security was the paper by Vazirani and Vidic in 2012. One thing I like about this field is the diversity of techniques. The techniques that were used to accomplish this were totally different from the classical security techniques. What they basically showed was if there were an insecurity, then there would be some way to deduce a contradiction. You could have the adversary use information from one box to predict the inputs of the other box. But by non-signaling, that's impossible. So that was done, but it left a loose end. And the loose end was the protocol that they were using had no error tolerance. It required certain perfect performance by the device. And so if it were a device with an honest level of noise, it would fail the protocol. So all this time, we were kind of working on our own tools. And then in 2014, we had a breakthrough, and we provided the first proof of full security with a positive amount of error tolerance. And we did that using some methods involving Renyi entropy, which I'm going to go into detail about later. Okay, and around the same time, Kudran and Yoon and then Chung and Wu proved methods for achieving an unbounded rate of expansion, whereas before the best was exponential. And they showed that you can cycle and do cross-feeding between two different protocols to get an unlimited amount of randomness. Okay, and then our most recent results cover all non-local games and achieve maximum noise tolerance in a sense in which I'll make precise later. Okay, so the talk's going to be basically just briefly presenting the results in a formal way, and then I'll try to go into some depth about proof techniques, because I'm hopeful those might find applications elsewhere. So here are the formal results. So we're going to use the following variant of Kolbeck's original scheme. This is basically a Bell inequality experiment. The difference is, since we're doing randomness expansion, we need to do it in a way that conserves seed. So instead of just playing a non-local game over and over again, we choose a certain fixed input for the game, and most of the time, we feed that input to the device. And then every now and then, without warning, according to some highly biased coin flip, we decide that instead, we're going to actually give it uniformly random device inputs and score it according to the game. The key thing is that the device never knows when it's being tested. So we're trying to compel it to behave well, even on rounds when we're not testing it. We do that, and then after doing that for n rounds, we look at the average score achieved just over the game rounds. And if that is above a certain threshold, a certain superclassical threshold, then we say the device passes. Otherwise, we say it aborts, no output, the device is not doing what it should do, forget about it. Provided an abort doesn't occur, then we apply a classical randomness extractor, which is supposed to take weak randomness and turn it into strong randomness. And we say that that is the final output of our protocol. So the current results now show basically that the security level for this, the noise threshold, is about as good as you could hope it to be. Kudran, Vidic, and Yoon, who originally introduced this protocol, showed that this threshold, WGA, that's the optimal score among devices that behave deterministically on generation rounds. The protocol will be secure as long as the noise threshold is above that level. And you clearly can't do any better than that. And then we proved in our most recent results that the same is true against an entangled adversary. And the number of bits coming out looks like this. It's a parabolic arc, and it's basically a function of how much of a violation you achieve. You get a certain fraction of a bit of randomness per round of the protocol when you extract. So one of the interesting things to come out of this is that this rate curve doesn't actually depend on the particular scoring function of the device. The only thing we need to know is the output and the degree of violation, and then we get a certain universal lower bound on the randomness coming out. Okay, so the techniques we use to prove this. It all comes down to this function, which I'm going to call the modified trace function, where you take a Hermitian operator, take its absolute value, raise it to the 1 plus epsilon, and take the trace. It's a lot like a probability function, but it behaves a little bit differently. And you can also think of it as a measure of the randomness of a state, denoted by a density operator. So if you have a density operator and its modified trace is 1, then it's completely deterministic. It's pure. Otherwise, if the 1 plus modified trace is very low, that suggests that the operator has a lot of small eigenvalues, and that means that it's a highly random state. So ultimately, this is what we're going to be using to test the randomness. And it's almost a norm. We can refer to it kind of like a norm. It basically has norm-like properties up to error terms depending on epsilon. Okay, so everything in proving security comes down to making device-independent assertions. And that basically means we want to be able to assert inequalities that are independent of dimension, that don't depend in any way on the particular behavior of the device. And all of our, pretty much all of our device-independent assertions come down to the following claim. This function, if we consider it as denoting the shape of a space, is a uniformly convex function, meaning you take two operators S and T that have the same modified trace and are far apart. Their midpoint has significantly less modified trace. And this has been expressed by saying if you look at the unit ball under this function, that unit ball has no flat surfaces. It's necessarily curved. And this is a device-independent assertion. The gap that is proved here is independent of the dimension or any other information about the operators in question. And that was proved by Ball, Carlin, and Lieb in '94 for different reasons. So here's how we interpret this in terms of randomness. So the idea is if you were to look at a state that's being measured, such as the state inside the device when we're carrying out that protocol, you can think of that measurement as taking the midpoint of two operators, the original state and some unitary transformation of that state. And then if it's the case that that measurement significantly changed the state, so if there was a significant amount of disturbance by the measurement, uniform convexity says that the modified trace has gone down. So what that means is high disturbance implies high randomness. So this is a way of kind of rephrasing the general idea of the uncertainty principle. So the more that the measurement changes the state, the more we must be adding true randomness to the state. So we'll call that the 1 plus epsilon uncertainty principle, and we can bookmark that because we're going to come back to it later. So here's that protocol, and we want to prove security for it. Here's a first attempt. Say that we had an inequality in this form, basically asserting that if the winning probability of a device is high enough, then there's a certain lower bound on the von Neumann entropy of the outputs coming out of the device. So in the most naive setting, this might be a good way to start. Von Neumann entropy measures, in a sense, the number of bits that you can get from a state. So we might attempt to use this to prove security. And it actually does work, but we need to put strong limitations first on the way the device behaves. So this is only, this is only step one. If we were willing to assume, there we go, sorry. If we were willing, so if we restrict ourselves for the moment to the independent, identically distributed, non-adversarial case, we assume the device is doing the same thing on every round. then this kind of inequality is actually enough to carry out the proof. And that's not hard to show. It's doing the same thing every round. This lower bound here tells us how much you can get if you have multiple copies of that same state. And so the result is you're able to extract pi of c times n extractable bits. So that's all good. And I'm going to call that type of function a simple rate curve because we want to build on that. Now, in the non-IID case, things get a lot harder. We need to allow all sorts of possibilities. The device can remember previous inputs. It can vary its measurements in between rounds. And whatever state it starts with, which could be some mixed state that is entangled with an adversary. And we still need to prove randomness from the perspective of that adversary. One of the neat things to find out is that the same argument, same type of argument works. It just requires modifying the quantities and doing a lot more mathematical work. Von Neumann entropy is a part of a larger family of entropies, the Rényi entropies, and they're just a little more complicated to express. So that would be the Rényi entropy of a density operator rho for a parameter epsilon. And the great thing about this is, though it behaves a lot like the von Neumann entropy, it is a property that von Neumann doesn't, which is that it actually proves extractable bits in the one-shot case. You can take a single copy of the state rho, and you can necessarily get extractable bits for it. Not so for von Neumann. Natural attempt to then would be to take the previous inequality we had and just try to prove some same inequality relating the winning probability to the Rényi entropy. Only problem with that is I don't know of any uniform way to relate these two quantities. The basic problem is that what we have here is a function that is essentially defined in terms of trace. Probabilities correspond to trace. And over here, we have a function that is defined in terms of the modified trace. And it's important to realize that even though they may look as if they're close, trace of rho to the 1 plus epsilon and trace of rho, they don't have a uniform relationship. Trace of rho to the 1 plus epsilon could be arbitrarily small in comparison to trace of rho. And since we said this was device independent, we need to allow for that possibility. So the solution to this that kind of evolved indirectly in all of our work is that we don't actually work directly with the winning probability, but we work with something similar. Okay, here we go. So this ratio, trace of the winning state to the 1 plus epsilon divided by the original state to the 1 plus epsilon, looks very similar to the winning probability, but I just added in 1 plus epsilons to it. And it has a lot of the same properties as the ordinary winning probability. But it's kind of general principle is once you start working with the modified trace, you're pretty much stuck with it. You're not going to be able to translate back to ordinary trace. So you kind of have to carry through the whole proof just using these two quantities here. Okay, so new definition. I'm going to say that a function is a strong rate curve rather than a simple rate curve if, for all devices D, you have the following inequality. I've replaced von Neumann entropy with Rényi entropy, and I've just replaced winning probability with 1 plus epsilon winning probability. And the key thing to call attention to here is this is a device-independent error term right there. Without that, this assertion would be simple, trivial. It's the same as the assertion about simple rate curves. But it's the fact that this error term can be, is device-independent that really underlies the security proof that we ultimately get. And we proved, generalizing our previous work, that basically any function that achieves such an inequality becomes a lower bound for the number of bits coming out of the Kudron-Wittig and Yoon protocol. This was a part of the proof I had the most fun with. It's gone through many stages of evolution, and in the current draft, it's fairly boiled down and simplified. And basically, it's kind of a series of half-page proofs kind of all put together. So where are we then? So basically, we've shown that everything comes down to proving that we have a strong rate curve. Once we have that, then we have full security for the protocol. So here's where we'll actually use the 1 plus epsilon uncertainty principle. Suppose that we had a device that had high 1 plus epsilon winning probability. We want to show that it has high Rényi entropy. If that were not the case, take the take the device and pre-measure it on whatever measurement it was going to use on input A. Now I've got a device that is predictable on input A, which means its 1 plus epsilon score has to be bounded. This is the threshold we use to bound devices that gave predictable outputs on A. And it applies to 1 plus epsilon winning probability too. So by our assumption, we've created a big gap here. We started with something that had high winning probability, it was well above WG, and we brought it down to one that has lower winning probability. So that means disturbance is significant. We've changed the state quite a bit, going from here to here. And the 1 plus epsilon certainty principle says that means that some device-independent randomness was generated in the process of making that measurement. And therefore, high 1 plus epsilon winning probability must imply high Renyi divergence. And we put that in formal terms using the actual function from the 1 plus epsilon uncertainty principle, and then we get the rate curve that I was referring to before. Okay, so basically as soon as we get a violation going above WGA, we will necessarily get a positive number of bits per round coming out of the Kujan, Vidic, and Yoon protocol. So mission accomplished. So for example, CHSH game, the optimal quantum winning probability is 0.853. WGA, that in this case corresponds to the best possible classical threshold, which is 0.75. So we have a gap of 10.3% to work with. And it means if we want to do experiments, we can allow up to 10.3% error accumulated imperfections in the equipment that we're using. So we now have quite a bit more leeway while still proving quantum security. Okay, so an addendum, since just connecting this to other talks that we've been hearing, this one application of this is we can get another proof of device-independent QKD. And that is basically taking the same protocol, but distributing it between two parties. DI-QKD is essentially the same thing as device-independent randomness generation, except we're trying to get the secret generated at two different places securely. So there are a few extra steps we need to take to make that happen. So start with carrying out the protocol as usual with two parties, and they can communicate as they need in order to check the score. You don't lose much information there because game rounds are rare. They only need to compare their inputs and outputs during game rounds. So that's okay, and not much entropy is lost. So Alice and Bob carry this out, communicating to determine the shared inputs and everything, and the frequency, and when the game rounds occur. And they check their outputs, decide whether or not to abort. And then at the second stage, Alice makes a guess at what Bob's bits are. And here we need to use properties of the game that go beyond just the classical security or deterministic threshold. So the idea is, for example, when we're playing CHSH, the optimal strategy for the CHSH game involves Alice and Bob outputting correlated bits. They don't agree perfectly, but they're correlated. So the definition of CHSH is if you have if your inputs are A and B and your outputs are X and Y, the game is won if the XOR of X and Y is equal to the AND of A and B. So Alice can make her best guess at Bob's bits by exploiting that. So if the input is 0 and 0, then their bits are supposed to agree. So she can say okay, well, my first bit is 0. I'm going to guess that Bob's first bit is 0. And then on rounds, game rounds, when later in the protocol, Alice finds out what Bob's input was. If the inputs were both 1 and 1, she will flip the corresponding bits in order to try to get what she wanted coming out. So it's a kind of procedure that will succeed a certain constant proportion of the rounds, because Alice and Bob have checked that there's a certain level of performance by the device. And so we'll at least be able to know at this stage that Alice and Bob's bits agree for a certain constant number of rounds. As long as that constant is something less than 1/2, then we can apply information reconciliation, where basically Alice and Bob share partial information about the bits that they have in their store. And they give enough information that each of them can determine what the shared string is supposed to be. But an adversary who starts with nothing would not be able to read that information out. And then lastly, they perform randomness extraction. That's exactly the same as before. They're just doing the same procedure on both sides. And the only added layer we need in order to prove security of this is that we need to show that the amount of entropy that's lost during information reconciliation, which is some proportion of n, doesn't exceed the amount of entropy that you get at step 1. And we can do that for certain games, so we achieve DI-QKD. Okay, so that's it for the results. I'll comment about a couple open problems that remain. I think my feeling is on a lot of fronts, we've kind of exhausted the current techniques and taken them as far as they're going to go. So if we're going to solve these remaining open problems, it's going to require some new creative techniques to bring the results even further. So first of all, these rate curves that we have, they're only optimal in the sense that they are non-zero over the largest possible range. But there's definitely a lot of improvement in the vertical direction, making them as high as they can be. Our first paper showed a rate curve that was high when you approached the optimal quantum score, but was low elsewhere. And our new rate curve has a large non-zero range, but is generally pretty low. We'd like to be able to figure out the best possible rate curve, which should, based on current evidence, be the same as the rate curve you get against the classical adversary. This will be important if we're dealing with games that have high output. All we have so far is like less than 1 bit per round of the protocol. But if we're dealing with a game that has 16 bits of output, then a lot is being lost. So I suspect there are stronger results that are proved there. May require delving more deeply into the tools we use, like the uniform convexity. Okay, and then lastly, parallel randomness expansion. If we really want to go all the way in removing assumptions, we can go to the point where we don't even assume the devices get their inputs in sequence, but get them all at once. And I was working on a larger cryptographic protocol where we actually needed this, and I didn't know how to prove it. So the thing is, so this is an example where we tweak the problem slightly, and then all the techniques that we have go out the window, and we just have to start over. So sequential non-local games and parallel non-local games are very different, and the techniques used to address them are also very different. One of the immediate roadblocks is that when you parallel repeat a game, a classical device can actually achieve, in some cases, a higher average score over the parallel repetition than it could over a single repetition. And so it's not even clear initially what kind of threshold we're going to need in order to rule out classical behavior. So that's another open question. Okay, lastly, I just wanted to mention, so all of this kind of fits in the general umbrella of trustworthy quantum information. And this year over the summer, we hosted a first workshop on this topic. And it was a lot of fun. We were fortunate to have a lot of great speakers. And as Professor Zhang was saying, we're going to do it next summer in Shanghai. And that's it. Thank you.
Okay, thank you very much. Questions?
Is the noise robustness for QKD the same as for randomness?
So the noise robustness in general would not be the same. And the reason being that if the device were too close to this cutoff, then you would, the amount of entropy arising would be low, while the amount of discrepancy between Alice's key and Bob's key would be high, and you wouldn't be able to reconcile while still maintaining randomness. Yeah, so basically the cutoff needs to be something higher, and it's an open problem so far as I know to invent techniques to measure that.
Okay. Further questions? Okay, there's one in the back, yeah.
Does your result apply to any non-local game?
Yeah, the current results apply to any non-local game. That was the main accomplishment of our most recent paper. So basically, this cutoff here, that is the correct cutoff for any non-local game, which means you can use the non-local game provided that there's a gap between these two quantities. Yeah.
Thank you.
Okay, another question? Yep, Matthias?
Since you have your result for any value that goes above the classical value, if I understand correct, for any game?
That is almost true, and there's a subtlety here that we actually kind of tripped over in our first draft. So for some games, this is the same as the optimal classical score, but not for all. So for example, for CHSH, yeah, it would be correct to say that we have random number generation for anything exceeding the classical score.
What is the definition of WGA then?
Of WGA? So it is the supremum of all scores that can be achieved by devices that are deterministic on A. So if we were to say something stronger and require that they be deterministic on all inputs, then we'd be talking about the classical threshold. But this is something that, in some cases, can be higher up than the classical threshold.
Okay, my actual question kind of is, do you get some sort of rigidity for all things that go above WGA? So can you infer something about the measurement operators?
Oh, okay. Well, that's a good question. And right off, I don't know the answer to that. I've explored going the other way, kind of using games for which we know rigidity and using that to infer information about the rate curve. But yeah, immediately I don't know the answer to whether you could assert for a general game that some constraints on measurements occur once you go above WGA. It'd be something interesting to explore.
Okay. Is there any other question? It's not the case. So thank you very much again, Carl. Thank you.